Okay, so we continue the carnival of operator algebra that one can see. Talk in the afternoon. Francesco who is going to talk about the key theory of the core of graph algebras.
Thank you, Gilles. Thanks for the invitation and for the introducing me. Yes, so let me start by giving some motivation. So the topic is, as you can guess, I'm going to say something about multiplicative structures on the case theory of some AF algebras, in particular those that are cores of graph sister algebras. So let me start with some simple motivation. Suppose your sister algebra A is continuous functions over a compact Hausdorff space, then okay, there is you can see every one-sided module as a bimodule. You can take, it makes sense to take tensor product over the algebra, and the tensor product induces a ring structure, a multiplication on a case theory of the algebra, which is the case theory of the space X. Okay, this works because the algebra is commutative, because you have a space. If the algebra is non-commutative, the case theory, and here today case theory is only case zero, because first of all, I don't want to complicate things talking about K1, and then in all the examples that I'm going to show, K1 will be zero. So if A is non-commutative, in general, case zero of A is only an abelian group. And it would be nice to have a multiplication that on K0 of A that in the commutative case reduces to what one would expect, to tensor product, balanced tensor product, or product of vector bundles from geometric point of view. So why do we care about this? Well, there is a very simple example, which is the following. Consider, suppose you have a disjoint union of two closed disks. Then you glue them along the boundary and you get this picture here, your sphere. If you compute K0 in both cases, you get as an abelian group, you get zeta square. But for the second space, the ring structure, in the first case, this is a zeta square also as a ring. You have a component-wise multiplication. In the second case, the ring is the ring of truncated polynomials. So these two are isomorphic as abelian group, but not as rings. So the reason ring structure does tell you something more about these topological spaces. Of course, for sister algebras, you have a finer invariance than just case theory. You could compute Elliott invariant and so on. But here, since in the classical case it works to have a ring structure on case theory, it would be nice. I mean, it is a natural question to see if you can do something also for non-commutative sister algebras. So the first answer that you can, a first naive answer, I will tell you in what sense, is that there is already a ring around, which is KK of AA. This is a ring, whatever is the sister algebra A, and it makes sense. But okay, first of all, you can compute it, for example, in the case of the sphere, and you don't get what you would like. So this is not, in the commutative case, is not the ring K0. So for the sphere, for example, this is just KK, the ring is 2 times 2 integer matrices. Okay, I'm going out so you don't see it. So it's not what you would like to have. And also you cannot expect that it is finer than the case theory groups, finer invariant, because for a large class of sister algebras, having isomorphic K groups means that the sister algebras are KK equivalent, so you don't get more information. Plus, it's not functorial and other problems. Okay, so there is a work in progress with Tomek that may or may not be online. Is not online. There is a work in progress on how to construct for arbitrary sister algebras a multiplicative K-functor. So a functor like this K0, which ends up in rings, it is really a functor, not like a KK. KK, the problem is that KK theory is covariant in one entry and contravariant in the other. So if you put the same algebra inside in the two slots, you don't get a functor. And okay, but I'm not going to talk about this today. So today I don't want to talk about how to construct this functor. I want to talk about a specific class of sister algebras where, questions from the audience? No. So today is more about examples, and I want to tell you for this next class of sister algebras, this course of graph sister algebras, what you can do, what you can say about the multiplicative structures in the standard K-theory. Okay. So another slide of motivations. Now let us focus on this example, the complex projective space of dimension n-1. This is one of the few examples where you can compute explicitly the K-theory. Well, no, there is a class of examples, but there are not so many where you can really compute, meaning that the K-theory ring, where you have a presentation of the ring in terms of generators and relations. And it is this is the ring of truncated polynomial. N equal to 2 is the one that you saw in the previous slide. So this is the generalization. This is something well known. It was computed by Atiyah and Todd. And this isomorphism between the K-theory and the ring of truncated polynomial is the one that sends the Euler class of some line bundle to X. So X, if you identify these two, X is 1 minus the K-theory class of some line bundle. L1 is the dual of the tautological line bundle.
What? One is the class of one.
One is the class of one.
L1.
L1 is the dual of the tautological bundle. And this difference is what we call the Euler class for line bundles. In general, for vector bundles, is more complicated.
Do you remember which it was?
64, I think. I'm not sure. Yeah.
That is a very beautiful paper.
Yeah. Yeah, it's a very nice paper. Okay, so now take call LK the case tensor power of this bundle L1. It makes sense also for negative K because line bundles are invertible. So, and L-1 here is just the tautological line bundle, the example of complex projective spaces. Then what you get from this ring structure is that in particular, if you take powers of X, the first n powers from 0 to n-1 give you a basis, and you can rewrite them in terms of the first n line bundles. So the classes of the line bundle from L0 to L-1 give you a basis of the K-theory as a zeta module. And you can take this relation x to the n to the power n equal to 0. You use the binomial expansion on the left. You use the fact that the class of L1 to the power k is just class of the line bundle Lk. And you can rewrite this relation in this form. Now, in this form, in this relation, you don't see the product in K-theory anymore. So this makes sense as an identity in the abelian group K0. The multiplicative structure is no longer. So what was surprising is that, at least for me and maybe also Tomek, Piotr, is that in a paper in 2015, Arici, Brain, and Landi guessed that these two things remain valid. These two properties are still valid for some class of quantum projective spaces, what are called here Waxman-Sobelman quantum projective spaces. So this was proved by them with some index argument by pairing K-theory with K-homology. Then there is another proof that uses groupoid sister algebras in a preprint with Piotr and other. I'm not listing all of them, but I can tell you who they are. So Albert Shaw, Thomas Maszczyk, and Bartok Zielinski. And this proof applies also to another class of quantum projective spaces that are called the multi-Pulbeck quantum projective spaces.
Excuse me, by LK, I'm sorry, by LK, do you mean L1 to power of K here?
Yes, yes. And if K is a negative,
yes,
L
I'm sorry.
1, you take L-1, yes.
Yes, I didn't pay attention at that conversion. Okay, yeah. I'm sorry.
Okay, so now the question is, first of all, what is these identities? It was a bit of a surprise that they still hold for a non-commutative sister algebra. What is the geometric origin? Since in principle you don't have a ring structure in K-theory, you don't have this thing here. And how general is that how general are these kind of identities in K-theory involving classes of line bundles? And so this is why I started to study this case of, to study these examples connected to graph sister algebra. So these quantum projective spaces studied by Rishi Brunellandi are both graph sister algebras and cores of graph sister algebras. So the frame is the one of graph sister algebras. I'm going to be maybe a bit fast on this because I guess many people, at least here in Florianopolis, are experts or have seen this. So by graph, I mean a directed graph. I denote by R and S the range and source map in this graph. E1 is the set of edges, E0 the set of vertices. A sink, I recall you that a sink is a vertex that emits no edges, like this one in the picture. An infinite emitter is a vertex emitting infinitely many edges, and I could not draw a picture because I cannot draw infinitely many edges. If you don't have infinite emitters, your graph is called rho finite. Now, I will only be interested in finite graphs, but let me give you the general definition of graph sister algebras because you will see it also in the next talk. So there is some sister algebra associated to a directed graph E, which is universal, is the universal sister algebra in a suitable sense, which is generated by a set of mutually orthogonal projections and partial isometries. You have one projection PV for each vertex V, one isometry SE for each edge E, and there are some relations. So these relations are that SE star SE, where star is the adjoint in the sister algebra, this should be the projection attached to the range of the edge. If you take all edges that are emitted by some vertex V and sum the range projection, you get PV. Okay, this is a bit confusing because these are range projections and the V is the source of the edge, but okay, this is just a convention. And this should be true for every vertex such that the set of S-1 of V is finite and non-empty, so that this sum makes sense. So no infinite emitters and no sinks. And there is one extra condition that is listed here, and you don't need it in the case of a finite graph, is implied by the other two. But in the general case, you need it. Is that for every edge, you take the projection of the source vertex of V. If you multiply this projection by S of V, you get S of V.
A question. So what is the sister algebra of your graph in green?
This one? Yes, this is a very nice question. If you want, you can compute it. I mean, the case theory is easy to compute, but then I don't know what is this sister algebra. But it is a nice picture because we have you see all the things that can happen. You can have parallel arrows, you can have double loops. Yeah, you don't have infinite emitters, but I don't want just to write, to draw an arrow with a sign infinite. When I learn how to draw infinitely many arrows, I will do it. Okay, so this sister algebra, this is a definition slash theorem because you prove that it exists. And this sister algebra is unital exactly when the set of vertices is finite, and the unit is just the sum of all vertex projections. So this is the unit of your sister algebra. I like unital sister algebras because they are the analog of compact Hausdorff spaces. So this is what I'm going to, why I'm going to work mainly with finite graphs. And also the edge set in my examples will be finite, also this E1. Okay, yes, so maybe let me go fast also on this. There is a grading. So let me forget for a moment about projection. There is a grading which is induced by an action of U1, but the grading is simple to describe because you can declare that every vertex projection has degree 0, every partial isometry SE has degree 1, and then you extend the grading in such a way that is compatible with multiplication, and you get the grading on your sister algebra. Lk is the set of elements that have degree exactly k. The direct sum of this Lk is dense in your graph sister algebra. L0, this grading comes from a U1 action, and L0, k here is an integer. L0 is just the subalgebra, sister subalgebra of elements that are invariant under this gauge action. This is what we call the core of the graph sister algebra. So the idea is that we think of this LK as the LK is what replaces line bundles in the geometric picture of projective spaces. It's a kind of a set of sections or module of sections of a virtual line bundle on the quantum space that is described by L0. So the geometric picture is that L0 is your quantum space, the core of the graph system algebra. The graph system algebra is like the total space of a U1 principal bundle over L0, something like that. And this total space, let's say this algebra of functions on the total space, decomposes as a sum of modules of sections of line bundles. Okay, now this grading, if your graph is finite and with no sinks, this grading is a strong grading, meaning that Li times Lk, Lj times Lk is equal to Lj plus k for all j k integers. And conditions such that your grading is a strong grading are in a series of papers that I mentioned here. Okay, here I put only the here, but if you Google or search on archive for the names and the years, you should find easily these papers.
Do you remember in which year Szymanski published his paper with the implication 108?
No, I think I don't Szymanski. No, I don't remember. I mean, I only remember these three papers, but these three guys. Maybe Szymanski was for a specific example, like yeah.
And he proved that if he is finite in those things, then he actually is free.
Okay, no.
But implication the other way around, much harder.
Yeah. No, what I remember is, I mean, in these three papers, first it was studied the case of rho finite with no sinks. Even in the case where your graph is rho finite with no sinks, necessary and sufficient condition is quite complicated. But if the vertex set is finite, then the no sinks condition is necessary and sufficient. So if you want a unital graph system algebra, then this is necessary and sufficient to have a strong grading. Okay, so anyway, a strong grading in particular, this means that every bimodule, each one of these line bundle is an invertible bimodule. Invertible means that you have a dual bimodule such that the tensor product over the algebra is isomorphic to the trivial one. And the multiplication, it also means that the multiplication induces an isomorphism of bimodules that transforms the balanced tensor product in the sum of labels, say j and k. Okay, so these are about line bundles. Okay, this is maybe I'm not sure we are going to need this, but let me remind you, we saw some of these formulas already in the morning. I denote by e to the power n the set of paths of length n in the graph, which means that you have a sequence of n edges, and each one, the range is the source of the next. If you call alpha such a sequence, you can attach to this alpha a partial isometry, which is just the product of the isometries of the edges. And if alpha is a vertex, you just define this as alpha to be the projection, vertex projection. In terms of grading, the degree of S alpha is exactly the length of the path. And in particular, LK is a module of sections of some kind of visual line bundle. LK is the closure of the span of monomials, S alpha as beta star, where alpha and beta, the difference of the lengths of these two paths is exactly K. There is you can prove that this monomial is 0 if alpha and beta have different range. And you can prove in the opposite direction that as beta star S alpha is either S mu if alpha is a mu concatenated with beta, S mu star if beta is alpha concatenated with mu, and 0 in all other cases. And this is basically all what you need in many cases to do computation and prove things about this sister algebra. So let's say you can reduce many proofs after a first part, maybe topological part, to algebraic computation in this with these generators. Okay. I introduced this because I wanted to give a few details about the core, and in particular explain. We know that the core of a graph system algebra, at least when the graph is finite with no sinks, it is an AF algebra. It's approximately finite dimensional. But what is nice is that actually, I mean, this is very explicit. You can find it, for example, in a Reborn book. You can construct a sequence of matrix algebras out of the graph, and it works like as follows. So for every natural number n, denoted by nv, v is a vertex, the set of all paths of length n and with range v. So n is the length of the path, v is the range. So the range means the range of the last edge. Okay, if your graph has no sinks, note that En is always non-empty because you can always extend a path. Any path can be extended and you get paths of any length. But ENV could be empty for some choices of N and V. If for some N and V this is not empty, then you can define an associated subalgebra of your graph system algebra, in fact of the F core, as follows. A and V is by definition the span of monomials as alpha as beta star, such that alpha and beta are in this set. I have length n and in the vertex b. So since the length is n for both paths, this is in L0 in this core, in this C-star subalgebra. And I don't put the closure here because we will show in a moment that this is a finite dimension. I mean, it's not that difficult to guess. If you forget about the range of the path and sum over and take the span over all paths of length n, you get something that denoted by an. An is just the direct sum in the algebraic sense over all vertices of the A and V. And so here the point is these elements, these elementary monomials are not linearly independent in the big algebra, in the graph system algebra, or even in the core, but they are, but the subset that you use to generate this A and V is an independent set. So for this A and V, these are really a basis, are linearly independent because the non-independence comes from the fact that you can always extend the path in, okay, we will see something, some clue about this.
I just managed to Google it up. So you should mention my here in one direction.
Okay.
In 2002, so it's like 11 years old.
Okay, so I was probably the references that was showing were for necessary and sufficient condition. Yes. Yeah.
I remember
yes.
We wanted to put the equivalence. We started writing a paper, certain areas, and then somebody, because it's very hard to find this result because it's directly in algebra. I mean, you don't see anything like even Levi's algebra.
No, but I think it is cited in this other paper.
Alex picked it out because but it's written in such a way that it grasps the algebra, non-primitive topologies, you would never find it.
Okay. Okay. Yes, so thanks for the 2002. Yeah. So it's the same year of his paper on Q spaces as graph system. Okay, so these are, let's go back to this slide. These elements form a basis of this vector space, and the map sending these elements to the matrix units of a suitable matrix algebra is an isomorphism of algebras. And that's how you see explicitly that A and V is a full matrix algebra, whose size is just the cardinality of this set, is the number of paths of length n with that vertex as a range. So this is an explicit isomorphism. This AN, the direct sum over all vertices, you can show that it is a subalgebra of n plus 1 for every n, and I will give you some clue in the next slide. And this means that you have a chain of nested algebras, one inside the next, and the union, the closure of the union is this sister algebra. Let's say closure in the norm of this core here. And in this way, you show explicitly that the core of a graph sister algebra, at least here is for finite graph with no sinks. Actually, row finite with no sinks is the same. But if it is just a row finite and you forget the no-sinks condition, well, then it is a bit more complicated, the construction. It is still true, but the construction is a bit more complicated. In the non-row finite case, okay, it's even is not always true.
Sorry, Francesco,
yeah.
Can you go back? Why do you here use the union instead of direct sum?
Because I'm thinking of these are by constructions all subalgebras of these, one inside the other. Yeah, they are one inside the other, and then this is just the union is dense in the algebra that contain all of them. For each n, you have a direct sum of matrix algebras. So each of these finite dimensional sister algebras is a direct sum of matrix algebras. And this is a direct sum. If you multiply two in different summands, the product is the 0. But this is not a direct sum. They are one inside the other. And I show you why in 1 second, because this is important if you really want to draw the Bratelli diagram. So I'm trying to give a bit, some details so you can play with the graphs and diagrams later on. So let me call gamma the adjacency matrix of the graph E. This is a matrix entries are labeled by vertices, and this is a finite matrix because I have a finite graph, integer matrix. Since E has no sinks, for every pair of paths alpha and beta as alpha as beta star, you can insert in the middle the range projection attached to the range of alpha. But now the range of alpha is not a sink, so you can use one of the two Cons-Krieger relations, saying that this projection is just a sum of SE SE star, is a suitable sum. Mm-hmm. And then what did you do? Here on the left, you have an element in the algebra A and V, and on the right, you have a sum of elements in the algebra AN plus 1 W, where W is any vertex such that there is an edge from V to W. So what's happening here is that your map sends each full matrix algebra A and V in the matrix algebra AN plus 1 W, such that V and W are connected by an edge. This gives you the Bratelli diagram, say at level n. Okay, so how is the Bratelli diagram of this AF algebra? How does it look like? So at the level n, you have several nodes, one for each vertex of the graph E. At the level n plus 1, again, you have several nodes. And one node from the level n is connected to a node to level 11 n plus 1 if there is an edge in the graph. And in fact, the multiplicity of the embedding is the number of edges. There are examples. I will show you some simple examples in the next slide. Let me just note that A0 is one-dimensional, A0 V for every V is just the scalar multiples of the vertex projection. So in the Bratelli diagram, you start, for each vertex, you start with a node that has a one-dimensional algebra attached. And okay, there are recursive formulas, maybe these are not important, to determine the dimension of each of these matrix algebra. The important thing is that, as we know, as who studied a little bit AF algebra knows, if you tell you what the Bratelli diagram is, you can compute the dimension of each of these finite dimensional algebras by simply looking at the diagram. So elementary examples. So let me start with this. In this graph has two vertices, one edge and one loop, and we know you can write down explicit isomorphism that the graph sister algebra is 2 times 2 matrices of functions on the circle. What is the Bratelli diagram? At level 0, you have the one-dimensional algebras attached to vertex projections. So this is the first vertex and this is the second. At level 1, you have an arrow from this vertex to this, which becomes this arrow. You have a loop, which becomes this arrow, and this is the first piece of the diagram. Next, here you don't have anything because there are no, the set of paths of length 1 that end at this vertex is empty. So you can either put 0 as, if you want, by convention as sister algebra, or just nothing. And this is true not only for length 1, but also 2, 3, and so on. So what happens is then that this becomes a constant sequence of 2 times 2 matrices. And okay, the inductive limit, the AF core is 2 times 2 matrices. So next example is take this graph, the cycle graph of length 2. Again, this is known that the graph sister algebra is the same matrix algebra as before, matrices of continuous functions on the circle. But now if you draw the Brattelli diagram of the F-core, you get the following. Whatever, at each level, you have two vertices. You have two nodes, one for each vertex of your diagram. And each vertex is connected to the other vertex in the next level. So you have these crossing arrows at each step. This is one-dimensional, is embedded here, which means that also this is one-dimensional. This is one-dimensional and so on. Each node represents a one-dimensional, if you want a sister algebra. You have a direct sum of C plus C at each level with a map from one level to the next that is just the flip. And the direct limit is C to the power. So you see, this is a very explicit. And I just wanted to point out with this simple example that one has to be careful because even if the graph sister algebra is the same, you can have different graph giving the same graph sister algebra, but not the same core, because in one case it's C2 and in one is 2 times 2 matrices.
But it's obviously because the isomorphic is not gauge equivalent.
Yeah, because it is not gauge equivalent. Yes, of course. Okay. Let me comment on the realization as a groupoid sister algebra. I won't say much, but just to show some examples. Suppose you have a relation R on a set X. I will denote by X over R the groupoid, this relation thought as a groupoid, because the philosophy is that it is a kind of quantum space replacing the geometric quotient in, this is the point of view of non-commutative geometry. So this quotient means the groupoid was arrows are given by elements in R and whose object set is X. And I'm sure that you saw the groupoid, this special case of groupoid, and I'm not going to say more. So every AF algebra, we know that it is a groupoid sister algebra, and the groupoid is an étale groupoid. What is the set of objects? The set of objects is the set of right infinite paths in the Brattelli diagram. The relation is the relation of tail equivalence, where two paths are tail equivalent, starting from some point they are equal. Okay, I'm hiding a lot of things because I'm not telling you what is the topology here and what is the topology here, but okay. Well, multiplication, this is a relation. So multiplication is you have a pairs and I can write it down. This is what I didn't want to do, but if you have a pair XY of elements in relation and a pair YZ of elements in relation, the multiplication is XZ. The usual one, yeah. Okay. So let me erase this. And the topology, especially on the relation, maybe is not that obvious, it's not difficult, but I don't want to spend time telling you what it is. But at least as a set, these R and X are quite clear. Okay. Yeah, in the following picture, I will add one vertex to the Brattelli diagram that is the root of the diagram, if you think of it as a rooted tree. And the point is that here, right infinite path is not like when you associate a groupoid to a graph sister algebra. In that case, the path can start from any vertex. Here, you consider only paths that start from the root, but you can pass from one to the other. I don't want to say too many things on this, and I will even skip this. Okay. So example one, I want to spend some time to tell you about examples. Yeah, sorry, maybe just a last comment. Maybe I should tell you, I should explain this. Here I'm hiding a lot of technical things, but everything is well known here. I'm not telling you what is the topology, but I'm also not telling you what is the sister algebra. Is it the full, reduced, and so on? The point is that all these groupoids are, well, not only étale, which means that the convolution product is the easy one that you may have seen with a sum, but they are also amenable, which means that doesn't matter. Reduced and full groupoid sister algebra are the same. Okay, examples. So let's take this graph. This is the graph of the Kunz algebra O2 that we already saw this morning. And what is the Brattelli diagram of the F-core? You have only one vertex, which means that at every level you have only one node, and you have two arrows from each node to the next one. So this is this is well known. It's the Brattelli diagram of the car sister algebra, where car is canonical anti-commutation relations. Label the arrows 0, the one on top, and 1, the one on the bottom. So if you label the arrows like this, now an infinite path, a right infinite path is just a sequence of 0 and 1s. And in fact, the topology is what you would expect. So in the groupoid picture, the path space, the infinite path space is just a space of binary sequences with the usual topology that makes it homeomorphic to a Cantor set. Okay, the relation is still a tail equivalence. So in particular, this car algebra is just the sister algebra of the relation binary of tail equivalence on all binary sequences. And it is highly non-commutative. Yeah. And okay, and this is one of those examples where the quotient space, this is an example for those who study these kind of things, of a minimal relation on a Cantor space. Minimal relation means that equivalence classes are dense. So the quotient space, the quotient topology is the trivial one. The quotient space is not interesting, but if you study the groupoid sister algebra, that has a lot of interesting properties, is a non-trivial. Okay, next example. Next example. Take the graph of, this is the graph of Voronovich quantum group SUQ2. This was proved by, I think, in the 2002 paper by Young and Szymanski. This is the first time that appeared. And this is the graph. Again, we play the same game. I put here a special vertex, which is the root, because I want to remember that all right infinite paths should start from the root. Then these are the vertices corresponding to the one-dimensional subalgebras of elements proportional to the two vertex projections. At each level, you have exactly two nodes. So at each level, the subalgebra n is a sum of two matrix algebras. The dimensions you can read from the diagram. And what is the diagram? If this is corresponding to the vertex on the left in E, and this is the vertex on the right, then from here, from the vertex on top, you can go here or downstairs. But from the other vertex, you can only go downstairs. This corresponds to the loop. You can play the same game and put zeros and ones on arrows. 0 if the range is on the top level, and 1 if the range of the arrow is on the bottom level. And the path space, again, the path space is just binary sequences, but not all binary sequences. You can have either the null sequence, or you have a sequence that can start with zeros, but then you go down and you stay down. Once you are down, you can never go up again. So either you have the null sequence or a sequence that is the tail equivalent to all ones. You see that now the quotient space, this is a bit different from what we saw before, because now there are exactly, the quotient space has exactly 2 elements. So there are only 2 equivalence classes, the one of 0 and the one of the constant sequence 1. This is not a minimal relation on a Cantor set as before, but still the AF core, which the interpretation is as the algebra of the quantum project, Waxman-Soibelman quantum projective line, or standard Podlish sphere is also called. Still, this sister algebra is the groupoid sister algebra of this relation. And actually now you can even write down explicitly the groupoid, which is the one that you see here. It's an action groupoid. Bar means 1 point compactification. It is a reduction of some action groupoid. Okay. Last example, maybe I'm going too slow. Last example is
these are 2 edges connected by counting link, 2 vertices connected by
counting. Yeah. I mean, the core in this case is also a graph sister algebra, but I usually never talk about the graph of the core. For me, the core is just something inside the bigger graph sister algebra. But this is also a graph sister algebra of an infinite graph, and here is the graph is just 2 vertices and infinitely many edges.
The minimum is based on property.
Yes, in this case is the true. Okay. So one more example. Take this graph here, and again, one loop and one cycle of length 2. You can prove, it's not completely obvious, but there is a nice geometric proof that this is the sister algebra of the Kunz algebra of 2. And the Bratelli diagram now is the one that you see below. You have again 2 rows of nodes. From the top node that here is correspond to the one on the left, you can stay on top or you can go on the bottom. But if you are on the other node, if you are in the bottom row, you can only go on top. You cannot stay on the bottom. Put zeros and ones with the same rule as before. 0 means the range is on the top level. 1 means the range is on the bottom level. And now what is now an infinite path, a right infinite path in this diagram? Now you have binary sequences where, well, 1 is always followed by 0. You cannot have 1, 1. Every 1 is followed by 0. This is the group, the AF core is the groupoid sister algebra of the principal groupoid given by tail equivalence on this set. And we know what is this. This is the what, according to Kohn, is the quantum space parametrizing Perot stylings. These binary sequences, these are exactly what we call index sequences of Perot stylings. 2 tilings are equivalent in a suitable way if the index sequences satisfy this tail equivalence relation. So this is kind of a moduli space of Perot stylings, but non-commutative. Again, you have a minimal equivalence on a Cantor set. So the quotient topology would be just the trivial one, would tell you nothing. Okay, so, and this is just to show my LaTeX skills, but okay, there is it is an example of Perot stylings, a portion of an example of Perot styling. I'm going very slow. Let me see. Okay, I have to go a bit faster. From now on, my algebra A is the AF core of a graph sister algebra. LK are the line bundles that we had before defined using this grading. And if you take not just modules, but bimodules, A bimodules, they still form a semi-ring, at least isomorphism classes of bimodules form a semi-ring under direct sum and tensor product. Semi-ring because like when you construct K-theory, I mean, you don't have inverse. This semi-ring has a sub-semi-ring, which is generated by this, that I will call a line bundle from now on. This sub-semi-ring generated by line bundles, I denote it like this. I call it Picard semi-ring because the group under tensor product generated by line bundles is usually called the Picard group. Now, invertible, these LKs are invertible bimodules. Invertible bimodules are automatically projective and finitely generated both on the left and on the right. So you can transform them, they have a K-theory class, but you have to choose if you realize them as a left or right modules. So for me, K-theory, an element in K0 of A is either the class of a projection or of a left module. I choose left for some reason. And using the fact that well, every bimodule in this Picard semi-ring is a left module, projective and finitely generated, I get a map like this. This map is a homomorphism of semigroups. So see, here you have a semi-ring, you don't have inverse. Here you have a group, but you don't have multiplication. But what they have in common is that they both are semigroups. And you have a map, which is not in general, not injective and not surjective. K1 is a 0 because I'm working with AF algebras, so I only care about K0. Natural question is when is K0 generated by line bundles, by classes of things inside here? And another question is there a natural multiplication here which is compatible with the tensor product of line bundles, so such that composed with this becomes not just a multiplicative structure here such that these maps can be promoted to a morphism of semi-rings. So that is the question. Okay, and then let's...
Obviously, these line bundles have this bimodal structure, so you do have a semi-ring, but nobody tells you that it's compatible equivalence relation in the big.
Yeah, and here you get, I mean, the map is well defined, and you have a morphism of semigroup. So here there are several special things that are happening. For example, AF algebras are cancellative, which is not always true, right? So two modules have the same K-theory class if and only if they are isomorphic, one and equivalent. So, yeah, isomorphic, the modules, yeah. Okay, so generators. Now the graph, I will assume that my graph is finite. Gamma is the adjacency matrix, N is the number of vertices, and A is the AF core. First lemma, if your matrix, adjacency matrix, is invertible over the integers, then K0 is just zeta to the power n as an abelian group. A basis of K0 as a zeta module is given by the classes of vertex projections. And you even have a formula that tells you each line bundle, how does it look like when written in terms of vertex projection. You have an explicit formula where here you have powers of the adjacency matrix. Yes, yeah, this is completely general. Now define a new matrix as follows. I call it gamma tilde, is a square matrix, but is labeled by pairs K and V, where K goes from 0 to n minus 1, and V is a vertex. Yeah, because it's less than n. Is greater or equal than 0 and less than n, and V is a vertex. Yeah. So except for the labeling, this is a square matrix. And how is it defined? What I do is I take the adjacency matrix power minus k, gamma tilde entry kv is gamma to the power minus k, and then I sum all the elements that are in the column v of this matrix. Okay. Now, because this is the point is that this is exactly the matrix that appear here in the formula that give you line bundles in terms of vertex projections. So now if not only gamma is invertible, but also gamma tilde is invertible over the integers, then you can take projections, you can invert this relation in some sense, and show that classes of line bundles from L0 to Ln minus 1, they form a basis of K0. So you just need these two matrices to be invertible, and then your K0 is indeed generated by line bundles. I'm going to show you some example very soon. But first, the next, last slide with the general results. Yes.
You see, this formula, which is just about a proposition, is very interesting to me because, well, there's an inverse, but if you take gamma to the power k, gamma to this matrix.
Yeah, it's the number of paths. Yeah, it's not a coincidence. It's because it's the sides in each in this matrix, in each row. You have the sides of the matrix algebra at a certain level, basically. But still, when you put all this together, I could not give an interpretation to this matrix. I mean, each row is clear what it means, but okay.
Excuse me, I have a question about the previous page. Yes, you say that if the adjacency matrix belongs to the GL and Z, then the K theory is the direct sum of cyclic group. So, for example, I wonder what is the
not cyclic group.
Matrix. No, K0 of A is the cyclic group to power of n. Okay, but I wonder.
It's integer. It's the group of integers to the power n. Is zeta plus free group.
Yes. Yes. Okay, but I wonder what is the corresponding matrix for the graph generating the Kunz algebra. In that case, for example,
I will show you, but that is not invertible. I will show you is one of the non-examples that will come in a few slides. So I will show you in a few slides what happens with Kunz.
For example, consider the O2. O2 is generating by two loop. What is the matrix? Is that matrix identically one and is
is the matrix with the 2 in the entry, which is not invertible. But I will show you in a moment. It will come. It's a very good question, but I will answer in a few slides.
Yes, thank you.
So let me just give. I will give this last general theorem and then examples. So gamma as before is the adjacency matrix. T is a formal parameter. Take the determinant of T gamma minus 1, expand this determinant. This is a polynomial, and call C0, C1, Cn the coefficients. This is an integer polynomial. Okay. So then you have for any graph C star for the AF core of any of these graph C star algebras, again under the same condition that gamma is invertible over the integer, you have a generalization of the theatoid identities that we were talking about at the beginning, and the explicit formulas are here. I mean, I'm not going to read the formula, but the point is that the class of each line bundle can be written explicitly in terms of the generators. and the coefficients appearing are exactly the one in this polynomial. Now, the formula are not that interesting, but they are used to prove the next theorem. So these formulas are the reason why you can prove the next theorem, and you need all of them. You need all of these expressions to prove what follows. So if both gamma and gamma tilde are invertible, then there is an isomorphism of abelian group from the K-theory of the F core to this, to the abelian group underlying this ring, zeta of t quotient by the real generated by this determinant. This map sends Lk, the class of Lk, to t to the power k. And is indeed, when you compose with the map from the Picard semiring to K0V, it is indeed an homomorphism of semirings. So you have a general formula for what you would call the K-theory ring in some sense. I mean, well, this is a semiring because you have isomorphism classes of bimodules. You can pass to the Grothendieck ring, but okay. I mean, you can do it, but I don't know if you still have a map to K-theory. You have to think about it because you have.
Well, the right-hand side is also Grothendieck group.
Sorry?
The right-hand side is also the Grothendieck group.
Of something, but yeah, but of different things. Because on one side you have isomorphism of modules, and on the other of bimodules. So.
Yeah, but still, I think it would be nice to have.
Yeah.
Instead of K0 of A, I would take this isomorphic classes before taking the Grothendieck.
Yeah, I mean, you can. It should be automatic. Well, I should think about it. It is possible that you get a map between Grothendieck rings, and the Grothendieck ring you could call it K-theory ring if you want. Yeah. 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 But still, I mean, for me, this is what I wanted to prove, that the important thing is that you have a multiplication which is not random, is compatible with this, and is uniquely identified by this property. So, but let me give you an example that this is what is interesting. So, peristylings. Peristylings, this is the graph. The AF core is this quantum space parameterized peristylings. This is the matrix gamma, and this is gamma tilde, and this is just a random coincidence that the two are the same, and it is both are invertible. What is the ring? The hypotheses of previous corollary are satisfied. What is the ring? The determinant of T gamma minus 1 is this one. And this ring is isomorphic to the ring of integers polynomials evaluated at the golden ratio. You just send T to the inverse of the golden ratio. So it's not completely obvious, but not completely trivial, but okay. You can also write down explicitly the Atiyah identities, and they involve, the only thing I want to notice is that they involve the Fibonacci numbers, which is something you would expect from peristylings, both the appearance of golden ratio and Fibonacci numbers. And okay, so this is the ring appearing in the previous theorem. Next example, quantum Waxman-Sobelman quantum projective spaces of dimension n minus 1. We saw this graph when n was equal to 2, only 2 vertices. Now this is the general graph. From each vertex you have n vertices, and from each vertex you have an arrow connecting each vertex to one which is on the right, and plus you have loops. The adjacency matrix is upper triangular with 1 on the main diagonal. It is invertible, and you check that also gamma tilde is invertible, but this is not trivial. There is some combinatorics to show that gamma tilde is invertible. Since gamma is 1 on the diagonal, T gamma minus 1 has T minus 1 on the diagonal, and this is the polynomial defining your ring. So what is the polynomial ring? For the core, yes. Yeah, because this is what gives me, it is the adjacency matrix of this graph that gives me the ring, not the matrix. So the point is that if you use the graph of the F core, you don't get anything. You need really this, because all line bundles are inside this bigger algebra. And okay, you get again the ring as expected, the ring of a truncated polynomial, and X is indeed the 1 minus T, where T is the image of this off-line bundle. You can also show that this line bundle, the K-theory class is exactly the K-theory class of the first vertex projection. And okay, and you get everything you expected to get. You have the Euler class of the expected line bundle generating this ring, and so on.
check whether in fact all these line bundles can be identified with their classes can be identified with perfect projection.
Yeah. Everything is a very explicit. I have still to.
The case theory of quantum projective spaces is easier than classical.
Yeah, because it's AF algebra. You have a lot of projections. And okay, now I give you one non-example and then one almost example, which is the cons algebra. So the cons algebra will come next. A non-example is, this is the graph of quantum length spaces, and the F core is what we call, the underlying quantum space is called quantum teardrop, is the analog. You have a U1 of Galois extension, which is the analog of the principal bundle from a length space to a teardrop. And here for every, yeah. And okay, so you write down, you can write easily down arbitrary power of the adjacency matrix. You can write down gamma tilde, and you see that second and third column are equal. So this is not invertible, except in one case when you don't have the third column. So it's not invertible if n is greater than 2. So this is one example where you cannot apply this theorem. And this is good because otherwise you would get the same ring as for projective spaces, which is would be weird. And now, yes, now Kunz. So this is, in this diagram, you have one vertex and n loops. So what is the adjacency matrix? Is a 1 by 1 matrix with n as an entry, which is not invertible if n is equal to 1. So this is not invertible. You cannot apply the theorem that we saw before. But even the point is that for some reason, even if you cannot apply the theorem, you can prove explicitly for this example, which is still many of the things that I said are true. It is a bit of, maybe, I don't know if it is a coincidence or one can generalize that theorem. So for example, you can prove that the AF core now is the UHF n infinity algebra. You can still prove that if K0 is an integer, and you take all line bundles Lk with K greater or equal than K0, then they generate the K theory. But they are not a basis because the K theory now is not a free group. Still, you can take any of these infinite sets of line bundles and you get the generators. And still, there is an isomorphism of abelian groups from the K theory of the F core to the same ring that I wrote before, which now in this particular case is the ring zeta of 1 over n. So it's integers polynomials evaluated at 1 over n. Or if n is equal to 2, this is the ring of d-adic numbers. I think it's called n-adic in general. So this is not a free group, which is the reason why you cannot prove that line bundles are a basis, but still they are a generator of this group. And this isomorphism of abelian groups still is compatible with the tensor product. If you compose with the map from the Picard semi-ring to K theory, you get the homomorphism of semi-ring. So it's compatible with tensor product. And this is the same map as before, is still Lk going to T to the power K. So basically you have most of the things I said before are still true for this UHF and infinity algebra, except that you have to change the proof adapted because gamma is not invertible.
Maybe you can adapt the general proof to non-invertible.
And but I don't know how to do it because it's very different. It's very different ways of proving. But I mean, they are very explicit. The point is that it's very nice. You can, yeah. Okay, yes. So thanks for your attention.
Maybe you could give a sneak preview in the multiplicative case.
Yes. So the idea in general, so one of the reasons for this work is that is that we have a general multiplicative factor, but then you want to compute it. And one point in these Atiyah identities is that this is what you need to compute then the K theory. So this is some preparatory work to compute the multiplicative K theory. So the multiplicative K theory, what you do is you have a sister algebra. You take for H A of algebra and or maybe I can say in words, I don't have to write down. So the point is that classically every vector bundle is associated to a principal bundle, which is If you want to work with compact spaces, is the bundle of unitary frames, for example, if you want compact version. So you have a compact principal bundle that can replace your vector bundle, and you can replace K-theory in terms of principal bundles. And the non-commutative version, obvious one, is that instead of principal bundles, you use off-Galois extensions, or maybe some kind of generalization. They can be off-Galois extension where the off-algebra is functions on a group, or the H could be a genuine quantum group. So the point is that classically you need only one principal bundle to generate the whole K-theory. Well, this is not completely true. Let's say that often you can, but I don't want to say when. But at least there is well, you have one SU2 bundle giving you all.
Not principal bundle. No, you have different bundles.
Well, they are associated to the same principal bundle, but with different representations.
I don't think so.
Yeah, but we can talk about this. Yeah, but at least if you can restrict to special unitary groups, you don't have to go farther than that, and you can define K-theory as some constructed with vector bundle associated to principal bundle with special unitary groups as structured groups and associated vector bundles. In general, the general definition involves what you do is for every off-Galois extension of your sister algebra, you construct a ring. But if you want to be sure that you get then the whole K-theory as an abelian group from this ring, then you have to take an inductive limit over all possible off-Galois extension of your algebra. And that's what makes it difficult to do computations, basically. So, yeah.
I know the answer to this one.
Yeah, sure. Yeah, I mean, I should have put at least maybe one slide about this, but it's a completely different talk, let's say. Yeah.
But it's motivation for calculation.
Yeah, maybe I can just show again the reference. Yeah, so this is the reference for multiplicative K-theory.
But no.
Not the last version, a new version will be online soon. Yeah.
You know the question from here? Any question online?
May I have a question?
Yes.
There is a famous graph which is not orientable graphs, and say Pythagorean graph. It is a tree, but one can impose some direction on the graph with some convention, and the Pythagorean graph can be considered as a directed graph. So, do you think that the corresponding CS algebra, which is obviously a non-unital CS algebra because we have infinite number of vertex, would be interesting for study?
Okay, so if it is a directed tree that you get at the end, it is a tree, right? So if it is a tree,
yes, it is true.
Yeah, so if it is a tree, you can prove that the AF core is commutative. Or in general, whenever you have a graph where each vertex has only one entry, then the AF core coincides with what we call the diagonal subalgebra, which is commutative. And actually, this is in the first part of this paper. And okay, it's not obvious that it's commutative, so I wanted to put the proof. But since it's commutative, okay, it's functions on some space, and you know that K-theory is a ring in this case. So the point is that I wanted the non-commutative example, not the sister algebra itself. The sister algebra in general is non-commutative, but the core is, the AF core is. Sorry?
Yes,
when you have a tree, directed tree, yeah.
Yes, I was talking about the Pythagorean tree, but imposing some direction. And just another question, could you please put the last page before the thank you page?
Yes.
Yes, the last page,
Before,
yes.
Yeah.
When you yes. What would behold if we add an exit on this graph, for example, find something? Yes. Is this an interesting CS algebra or trivial option?
Well, if there is only one loop, this is the Toeplitz algebra. If there is only one loop, if
no,
there
we
are
have
many...
a lot of loop. No, we have a lot of loop, but we add another exit as you just draw.
Yeah. So, I mean, this, if you have only one loop, this is the Teplitz algebra, but already this, I'm not sure. I don't know what it is.
We studied.
Yeah. Yeah, but is it something known? No.
I cannot tell you what system.
Yeah. No, we don't know what it is. I mean, it should be interesting, but we don't know. Yeah.
Yes. And finally, can you share the PDF of your talk? It was very interesting, and I need to read it again.
Yes,
maybe
so I think you will put it online. Yeah, that maybe, I don't know, you will announce the website, the same mailing list for the conference. I don't know. Yeah, so that there.
Tomorrow.
No, sure. There will be a website with all slides online. And okay, at some point, not immediately, in a few days, but you can just write one of us if you don't see it. Before the carnival, yes. Or you just write me and I send you the slides. It's not a problem. If you just send me an email, I will send you immediately.
Yes, I'm just sending you an email. Thank you for this very beautiful talk. Thank you. Thank you.
Bye.
Any other question online? I have some questions as well. So the fact of being strongly graded is something that's needed in the middle of groups, or?
Well, what is needed is that if you have invertible gamma, right, it means that you don't have any sink and you don't have any source, because no row is 0 and no column is 0. So automatically you get strong grading. But it is important because you want to map these line bundles to K-theory, right? And you need this line bundle to be projective and finitely generated. And for this, yeah, if they are invertible bimodules, automatically are projective. Invertible bimodules is implied by strong grading. It's not necessary, but is sufficient. But in any case, you cannot avoid it because you want gamma to be invertible at the end, which means that you don't have any sink. And the vertex set is finite because I'm working with unital sister algebras. So it's.
Yeah, I'm just thinking about all the algebras where you have another natural grading like algebras, and there's something that can be done with all the kind of algebras as well. It's need to check with the conditions algebras also.
I mean, in the paper, what I'm presenting is not everything. There are intermediate propositions that where you don't need invertibility of gamma. But for this last, yeah, I wouldn't know how to generalize it. I tried to think about it. For example, you see the Gunz algebra. It's clear that sometimes in some example, you don't need invertibility. I don't know why now it's out of focus, but okay.
I make comments to the question. Take the Teplitz algebra, take the gauge algebra, and it's not free. The thing, and it's not free. And you shouldn't expect it to be free because that's a quantum distance algebra. And you know that if you have a contractible compact topological space, the only free action of a finite group or say a compact group is the trivial. Nothing else can act free if you have a contractible space. Yeah, this is kind of like force Coulomb stuff. But there is a beautiful quantum effect. If you restrict the gauge action to the cyclic group, then it is, which is not the case classically. I mean, classically, no. The only group that can act freely on a contractible space, a compact contractible space, is the trivial. All other compact act non-trivial. I mean, they cannot act free. There's always a fixed point. But for the quantum disk, there is no fixed point if you restrict the cyclic stuff.
So, but maybe I have one comment for you, because you mentioned this morning this generalized grading, right? So this is the same as the Gunz algebra, the one on perostylings. If you use this isomorphism to see what is the disgajection for the other algebra, so basically what you are doing here. So basically you declare that one edge has degree 1 and the other has degree 2. And if you do this, if you use this modified gauge action, then you get the F core is the one of perostylings. That's why I was asking, maybe in general, it is interesting to study this course for different gauge actions.
Oh, yes.
Yeah. Yes, that is the one where you get, which is, I mean, this is also something expected because as an ordered K group, right? If you computed a dimension group, that is the one giving you the realization, giving you the correct positive cone. Positive cone is a polynomials with positive coefficients, right? Is a zeta of the golden ratio. Yeah. Yeah, because the transition matrix from one to the next is the one giving Fibonacci numbers and in the limit the golden ratio. Yeah.
Any other questions? So let's take Francesco.